Okay, so welcome everyone. My name is Pavel Smirnov. I'm a software engineer at IQM in the design and simulation team. And we're working on this open source design tool called KQCircuits, which is we've designed to be a plugin to KLayout, which is also an open source layout viewer and editor. And our focus is that we provide the tools to design superconducting quantum processors. And here is a slide that we've made that kind of showcases the overall life cycle of the QPU design process, and also specifically outlines at which stages the KQCircuits is useful during this design process, and at which stages it actually doesn't provide support. So I guess here I should specify that since GPU designs are starting with coming up with a Hamiltonian or designing a Hamiltonian, after which that Hamiltonian is then kind of we derive a circuit out of it. And for these two first stages, KQCircuits does not currently provide any kind of tooling. But once you have your circuit designs and you're ready to implement that circuit into a layout, that's where you can actually start using KQCircuits. And we've designed KQCircuits in such a way that we provide a library of elements that could be used in the superconducting chip design. And usually how the chips are designed is that they're kind of compositions of separate elements that you place at different places of the chip and then connect them together with waveguides. And once you have this chip design ready, before taking it to fabrication, you can first validate it. So we provide tooling to export netlists to verify that the netlist corresponds to the circuit that you've originally designed. And also some DRC checking, design rule checking, so that waveguides don't cross each other and elements don't overlap in such a way that prohibits actual chip functioning. And also what you can do is that you can take the full chip or portions of the chip, convert that geometry into something that a third-party simulator can use. For example, ANSYS or Elmer is also an open source alternative third-party simulator. And then once you run the simulations, you can then verify that you have all of the physical characteristics of your chip in order. And after validating that, you can then have more confidence into bringing those chips into fabrication. Then before fabrication, KQCircuits also provides tooling to compose a wafer mask layout, where in this grid style composition, you can place all of the chips that you want to fabricate during the fabrication round. And then you can send that file into a foundry to get your chips fabricated so that they can dice the chips out of the wafer and then can be used for measurements and all the stuff that you need to do with the chips. So that's pretty much what KQCircuits provides support for is composing a geometry, performing some validation in a simulator space, and then converting the chips into a mask layout. I guess I could give some quick notes about how the preceding stages work, how you can take circuitry into layout. I don't have too much expertise on this since I don't really have a physicist background. It's mostly software for me. But just something to relay from my coworkers is that here is an example of a Swissmon qubit that has been designed in a circuit in this kind of way. And I guess that translates in the layout like this. So here you have the drive line being coupled with the qubit, and then you have here a squid and a flux line that drives the squid. And here's, I guess, another example of the qubit. I haven't really seen this kind of qubit, so I can't comment on this much too much. But it seems like this might have even two islands in here. But just a quick note on how kind of, you take the transformation from circuit level into layout level. And I guess also here, there's a slide about what the transpond qubit is. So here you can see an example Hamiltonian of that was kind of come up with to get the transpond qubit implemented. And I guess the main point here is that we're designing an LC oscillator such that it introduces anharmonicity. So in the quantized energy states, the jump from zero levels, zero energy state to one energy state takes a different amount of energy than the jump from 1 to 2. So that way you can implement the binary operations within the qubit. That, my understanding, is the main philosophy behind implementing transpond qubits. Okay, but I guess that's enough about theory. So now let's get started with installing KQCircuits. I will do it live in this demo. So first I'll show what K-layout looks like. And K-layout is something that you can download from here. Hopefully the font sizes are okay and doesn't need to be increased. Hopefully you can see them okay. But the website is klayout.de. I guess it's under a German domain name. But this is the website for the K-layout, and you can press the get K-layout, and then depending on your platform, you can download, in the case of Windows, you can download an executable installer. And then for the Linux distributions, you can get the Debian packages that you can install. So I have that pre-installed for this demo, and it looks something like this. What you actually can do is that you can already start trying out KQCircuits, because when you open K-layout's own package manager, and if you scroll down, you will actually see KQCircuits provided as a plugin. But this is probably not a recommended, if you want to actually do something useful using KQCircuits, this is not a recommended way of installing KQCircuits, but something that you can do very quickly if you want to tell your friend about KQCircuits, for example. So after clicking this, okay, maybe there's already a demo effect. I think like this apply. Okay, you have to double click it, and then when you press apply, it will immediately start downloading and installing KQCircuits as a plugin to the K-layout. Okay, but this is not the recommended way of installing, and I'll show the recommended way. So the recommended way is to use Git. So hopefully you are familiar with what Git is. It's a version control software that most programmers use. And you can use this Git tool to have like a live version of KQCircuits downloaded in your system, and then you can also use the Git version tool to then fetch all of the updates that we periodically send into the KQCircuits repository, so you can always have your code up to date. And there's also branching operations that you can do in the KQCircuits. So if you have your own features, but you also want to be up to date with the features that we provide, then you can use so-called rebase and merge operations to be on top of it. And so the way to install is that you take this, you copy this URL to clipboard from here, and then in your terminal, I've made this folder demo. What you can do is that you use git clone command, and then you put in the URL, and it will start cloning the KQCircuit source code into your system. Shouldn't take too long. Yeah, that's already there. So now you can go into KQCircuits. Another thing that I highly recommend is to use virtual environments. So I made one here. It's called this demo env. It's a virtual environment. If you Google then it will tell you all about it. So you can create virtual environments, and then all of the dependent libraries that you need to have KQCircuits working will be in that one environment that you can activate and deactivate. And if you have other projects that kind of gets messed up by the dependencies that get installed, then you will have like a separate silo of dependencies here. So I will now activate my demo environment like this, using activate. And this kind of prefix in this terminal tells me that I'm using this virtual environment. So now that I've cloned KQCircuits, there is a kind of two modes of how to use KQCircuits. One is called KQCircuits as a GUI tool, and the second is KQCircuits as a standalone package. So here I will show how to install KQCircuits as a GUI tool. So you have to put in Python setup within klayouts.py. This will be provided in the KQCircuits folder. So you run this, it will create some symbolic links. And what this does is that next time you reboot klayouts, you will see some new stuff. So first, what you will see is that it already opens layouts, an empty layout when you boot it up. And also you'll see that here in the left bottom panel, you will have several libraries like chip libraries, element libraries, stuff like that. Also at this time, it's probably good to remember that from this setup, what you should have is that when you take this editing mode, make sure that you have the check mark in the use editing mode by default. So that makes it that you can actually edit layouts in the K layout. I think by default, when you install K layout, it only assumes that you want to view layouts, but make sure that this is turned on so you can edit chips using K layout. So now we can actually have a look at what we have in the element library. So this is something that we call smooth capacitor. Here I'll probably also say what kind of buttons I'm pressing. So I press F2 to kind of center the view. So anything that's placed in the layout gets justified within the window. And then you might have seen that at first it looked invisible and then it kind of popped into visibility. This is because we define a lot of geometries based on hierarchy levels. And usually, at least in the paradigm of how we design in KQCircuits, we just usually want to see the entire full hierarchy. We don't really we don't really show one layer at a time. So to show the full hierarchy is you have to press the asterisk button and actually in here display full hierarchy. This is like the same equivalent command. So whenever like you think that you can't see stuff, just make sure to press asterisk, and usually that solves the problem. But okay, here is one element that we have. We have a launcher, looks like this. This is something that we put on the edges of the chip so that we can then drive signals into the launcher, and then this connects to a waveguide that will then move the signal towards an element that we want. We have some TSVs here. You need to kind of connect signals from the top substrate to the bottom substrate. And then we can have a look at some of the qubits that we provide here. So for the open source variant, we've designed these double pads qubits. Here's an example because this one is supposed to show a squid, but it seems to be hidden beneath the bottom hierarchy level. So if I now press this full hierarchy or asterisk, now it will show me like this squid, which is like this kind of element that is important for implementing a circuit where I guess it induces flux in the electric field. Yeah, and some other qubits. This one Swissmon that I've shown in one of the slides that we provide, and also there's this concentric chat one. And all of these are defined as their own Python classes, and we can have a look at the code soon. But all of these can be modified if you want, or you can also create your own library of qubits. Yeah, and I guess another thing is I can show is the library of chips that we have, and I guess I'll just use this utility here. since this does a nice little layout of all the chips that we have publicly available. So these are the chips that get provided with the KQCircuits when you clone them. So here, I guess, is like a test chip used to kind of test the fabrication of air bridges in your foundry. Here's an example. I guess this is a lithography test. So here it tests the accuracy of your etching device. So there's like beams of different width, and it will tell you if they're accurate enough for your fabrication processes. Another one, if you want to use a flip chip configuration where you have two chips stacked on top of each other. And then here's a quality factor, which is a chip that contains resonators. And if you've carefully designed these resonators so that you know their resonating frequencies, then you can test that your fabrication round corresponds, the resonator resonances correspond as fabricated to the design frequencies that you wanted. But here, I guess, is an example of like a actual chip with qubits that can be controlled. So it looks something like this. In this device, there is like 6 qubits here. There might have been other, yeah, I think in this one, there's actually like a drive line, but also a flux line, a waveguide that connects to this squid. So you can also control the flux of these qubits. So I recommend to check out what these chips do, if they could be useful for you. Okay, so this is GUI of the KQCircuits, but also you can install it as a standalone. So to do that, I actually have to look up the commands that I have to input. And in this GitHub page, we also provide a documentation page. And you can click from here. And here you can have a look at the guides. Let's see if I can move this browser a little bit. Like this. So actually, most of the installation instructions that we have, we put under this developer guide chapter. And in here, this was the install instructions that we actually did just now, like using the setup within KLayout. But then this standalone usage, this is something that you want to use if you don't want to use KQCircuits in as a plugin to KLayout, but instead as a Python package that you want to integrate within your Python code infrastructure. This is also possible because KLayout also is provided as a standalone package. And in this demo, this will be useful whenever we will export simulations and masks. So this will definitely be useful for us in this demo as well. So to install the standalone package, what you need to do is just pretty much copy and paste this command here. So this will include KQCircuits as a package to be used in pip, but also install all the requirements that are needed. And here it also specifies not only that the core requirements, but also requirements that you need to build documentations, run unit tests, run notebooks, and run simulations. So now if we copy paste that, it should then provide all of those libraries within your virtual environments pip wheel. Downloads and installs a bunch of stuff, and eventually everything should be okay. Yeah, there it is. So one way to check that you have that installed is that when you run pip list and then you scroll up, you'll see this entry for KQCircuits, and it also points to this folder where you have KQCircuits cloned. So this means that whenever you make changes into the KQCircuit source code, it will actually be reflected in whenever you import KQCircuits in your code and like you actually use KQCircuits as an API. Okay, so that was that. Yeah, I guess coming back to this GUI thing, one thing that we encourage whenever you design your own elements that you need to use is that we encourage the use of parametrization for your shapes. So this shape of the smooth capacitor is not the only shape that you can use for all of your chips. You can probably even see it here. I guess these are not smooth capacitors, but they're capacitors of some other kind. But the important thing to note here is that this is the same class of capacitor, but the shapes are different. This is because in this capacitor, we've introduced a lot of parameterization of its shapes that setting different parameters to different values will give you a drastically different shape between those two. And I think this is something that aids this kind of rapid development, where instead of kind of redrawing the elements, whenever you find that you need to have a different shape, you just introduce a parameter, you change a value to it, and it will draw a different shape for you. And you can see the different parameters if you double click this element. And if you go into P-cell parameters, so here, for example, let's see if I can, yeah. I think there was, we can, for example, change the width of a finger. The finger is this little finger right here. So we can make it wider, and then we should immediately see the change that happens when we change that parameter. I guess the gap is something that can be changed. So here, the positive space means that we're going to have gaps. So we're going to etch away metal from it. And then everything that's white, that's negative space, that's where the metal is going to be. So here, when we increase the gap, we're increasing the blue space, so to speak. And I think like a very funky parameter is this one. I guess like one thing I can also recommend is that you show parameter names, because we give like this human readable name to the parameters, but we also in the code, we mostly refer to these parameters given by their like kind of coding name. But since these two might not be obvious to infer from each other, it's probably best just to kind of use this K-layout tooling where you show the parameter names. So then you can see like this finger control is something that we want to tune, and then in the code you can use a finger control. So here you can see that there's like 2 fingers, which translates to 2.1, I guess. So if we increase this to 5, this will kind of increase the number of fingers used here. And then also using kind of these floating points, you can kind of adjust this in a continuous way as well, as this approaches 4 fingers and stuff like that. So this kind of gives you an idea of like how these shapes can be parametrized so that you can have you can reuse the same element in the same chip, but in different places and having a slightly different shape. Okay, so let's actually try to design a chip using this this KQCircuits tool. So using your favorite code editor, I use Visual Studio Code. You can actually open the folder that contains the KQCircuits code. And one cool thing about Visual Studio Code that we support is that you can actually open the elements that you are designing from the source code just by running a shortcut. This is something that we provide support for Visual Studio Code, but also PyCharm. And there was like a hackathon implementation by an open source community to have this working for Vim as well. But we're a bit limited in how many editors support this feature. But I will show you what the feature that I'm talking about. So, no, not here. Oh, actually, okay, this one. So in this util create element from path file, this is the file that allows you to kind of give as an argument the elements that you want to open. So I guess I'll show you the code structure a little bit. So in this K-layout package, Python KQCircuits, we have this chips elements qubits thing, which you might recognize. the same way how we categorized these libraries as well. We have chips, elements, junctions, and qubits. So these correspond to each other. Like in this chip folder, we have all of the chips that I've showed you just now. You have elements that you can drag and drop and stuff like that. And you can, for example, open the smooth capacitor and see the source code that was used to derive this that shape that we were playing around with. And what this create element from path script does is that given the file location, like this one, for example, you can then invoke k-layout to be opened, so which will only place that one element alone in the layout, and you can see how it looks like. And this is something that's very useful whenever you're in this iterative process of developing the element that you want to implement. And instead of like running this in the terminal all the time, what you can do is that you can configure your code editor to use it as well. So what you need to do is that you need to copy and paste this piece of code. There's instructions here. So you have to create this .vs code folder. Let's see here, new folder, .vs code. And then here you have to create a tasks.json. And then just copy and paste this. And then you kind of have to remove all of these hashtags. So replace all of this. There's some comments here, a little bit of tinkering. I apologize for that. But I think now it's in good shape. So now what this means is that we configured the Visual Studio Code in such a way that using Ctrl-Shift-B, it should have a shortcut set up so that it will open k-layout in just a second, and it will only show me the smooth capacitor. So if you make changes for the smooth capacitor, let's see what we can do here. We can probably like disable something. Or actually, let's have a look at the qubits, since I'm more familiar with that one. So we have double pads. And when we open it right now, it will just show me 2 pads on the double pads like this. But let's say for some reason I decided I want to have 1 pad. So what I can do is find like this line of the code. I disable the second island. Maybe I make sure that, well, actually, what I'll do is I'll just remove this part here. Okay, and now when we run it, let's see if it made the change that I wanted. Yeah, so it doesn't have the second island anymore. So this is something that you can use. You can always iteratively make changes in your code and then immediately see what the change was that you made. And this is something that we will use in the later parts of the demo. So now let's actually go into designing our chip. So here, for example, I'm looking at this launchers chip, and let's check it out, what it looks like. So it's just an empty chip that has launchers on the side. So I think this is perfect because I kind of don't want to reinvent the wheel with how we place the launchers here. And I'm intending just to kind of place some elements into this chip and connect from the launchers into these elements using waveguides. So this is something that I want to do. So what you can do here is that you can copy this launchers file and paste it. Rename it somehow. For example, I can call it my chip. Also means that you have to rename the class as well. And you can actually see that this works already. So it shows me the same chip. And then also, if you look at the chip library, you can actually see that there's a new entry for my chip already that you can drag and drop here, for example, if you want. Okay, but Yeah, actually, let's run this again. So now I want to place stuff into this chip. So looking at the qubit library again, let's say we have these concentric transmons. I place one here and then maybe a second one here. So these are like transmons that we want to use in this chip. And then I want to connect them to the launchers. So the waveguides that can be placed here is something that we call waveguide composite. So when you drag and drop them, they kind of look like this. Maybe they don't exactly make sense at first, but these are very flexible elements. These are something that you can stretch and you can like place elements in between this waveguide. So in KLA, something that is provided is this partial tool. Here you can see that this element consists of like two vertices here. And using the partial tool, you can actually stretch the vertices. So it's you can actually like make this waveguide into like a waveguide-like shape. And you can also introduce in between vertices as well and move those around. And then it will create like a bending angle here as well. And another tool that you can use is this edit node. So once you pick the node, you can edit some of the features of this node. And here we kind of provide it as a default that one of the nodes will have this air bridge as an element. This is something that we can remove. So we can have this as empty. You press apply, and it's just a plain waveguide here. So now we can actually shape this waveguide to be connected with this qubit here. So one thing that's nice to have is to have these ref points. So you know where are the points where we want to connect the waveguides. And let's start shaping this waveguide. So we place here right about, and maybe one here, or maybe move this vertex here. Then we get a little bit closer. And it's a little bit hard to see, but here is a point indicating where we want to connect it to the launcher. And then it's another point that's kind of the corner point of it. So this is to make sure that the direction at which this waveguide comes into this launcher aligns well. So if you just kind of make it like this, there's still kind of like this, because the direction is not entirely aligned, you're gonna cause like gap here and then some jagged edges here. So this is where it's good to use this corner point as well. So if you introduce a new point here, and then you place it in this reference point, you will actually align it better. So that is perpendicular to the launcher. At this point, you don't have to be completely exact because you can go crazy into getting this accurate. We're gonna actually have a tooling that will help you snap the points together so that there are no gaps. And let's also connect the other point, the other endpoint of this waveguide to this qubit as well. So we're gonna connect it like this, and then we also will have it like this. And I guess this is a good shape for now. Okay, so we've made some changes into the chip. Let's actually convert that into the code so we can kind of like save our progress. So in the macro system, there's a macro editor in the K-layout. There is this, it usually starts with this Ruby panel, and then the interpreter here is Ruby. Make sure everything is in Python because all of our code is in Python. And in this local Python branch, you will also, you will see that there are these KQCircuits provided scripts that you can use. So you look into the KQCircuits scripts, and then there's macros, export, and then this export cells as code. And this is something that you can use. You just, if we run this now, it will generate some code here that you can immediately copy and paste into a new macro if you want. And it will actually like generate the exact same thing that you've just had in the layout. So let's actually do that. So we copy this, we paste this, so we can run this. And then in this new layout, it will have the exact same thing that we have here. So this means that this is now Python code that completely implements the design that you've just made using the CAD software. But it does some a little bit of adjustments, which are actually good. So for one thing is that it actually does snap the ref points. So now this waveguide is exactly aligned with this launcher. This is something that we didn't have here because there was a little bit of a gap here. So using this tool, we can also, it also makes sure that the intended snapping, it actually does snap. So there is a complete continuity with how this waveguide is connected to this qubit. So there's kind of different implementation ways of this Python code. We've used this mode called create plus macro. But if you actually want to have like a chip class that you can then include in our project file structure, then it's actually recommended to use this insert cell mode that we have here. We provide the documentation on what all of these modes do in the comments. But I will show here in the demo what is the preferred way. So now that we have, we set it to insert cell, we run this macro. Make sure actually to use this play button that has a exclamation mark here, because this other play button doesn't really work. And also another thing is that there is this bug icon. Make sure to disable it. It's some debugging utility that KLab has, but we didn't really find it useful, and it only slows down the macro performance. So it's best to just turn it off. Okay, so now that using this insert cell output format, we actually have these this codes that we can copy paste directly into the chip code file. So we take this, we go back into our editor, and then inside this build function, this is where we can like start pasting the code that we want to use. We can actually remove this my chip part because this already defines the my chip. So what we have here is that we have this one transpond, the second transpond, and then the waveguide composite that connects to the first qubit. So now we actually can run this code from here to see that we've effectively saved our progress. So closing all of these K-layout windows. Now we open a new one using the shortcut Control-Shift-B, and it will run this chip code and it will show us, okay, so there's some error, I guess. It's good to look into the logs. So where was it? Log viewer. Concentric transpond is not defined. Yeah, I think I forgot some of the imports. Yeah, I actually didn't copy the imports here. So yeah, let's actually try to remember them from hand. So it was KQCircuits dot qubits dot concentric transmon concentric transmon import concentric transmon. And then also waveguide component. Actually, like I'm going to cheat a little bit because I've had the working code file saved up for this demo. Okay, why is it not opening? Okay, so demo. This is actually the one that I prepared for this demo. So let's copy the correct imports here. So the concentric transmon, we copy it here. I actually did write it correctly. And then let's have this waveguide composite. Okay, so now that we have all the things imported that we need, I think it should now generate the chip correctly. Let's see. Okay, still some problems. Let's see. POA, okay. just a second. So we need to, copy all of these imports. So we don't have to think about them anymore. Okay. So now it should work. Still something. At least we can see the qubits now. W and base. Okay. So let's have a look at what the ref points are called. Okay. Okay. So somehow it doesn't really use the ref points that we have here. I think actually if we remove this my chip prefix, now it should start working. Okay, there it is. So now it's exactly the chip as we designed it in the GUI tool. And here I encourage to use this paradigm where you do kind of these broad strokes of the chip design by hand using the GUI tool. You convert that into code, and then you do like this kind of tinkering of the values, like cleaning up the values using the code. Okay, so now we can actually continue with this design. So we can do like other stuff. We can actually turn this waveguide into like a probe line from which we can branch the waveguides so that the same probe line can like connect to two qubits using splitters. So what you need to do is that you take this, the cell structure in this layout is that you have a top cell and then the actual cell of the chip. So make sure that you have that showed on top, and then so you can actually edit the chip elements that you've opened from code. You have to use this edit cell, convert cell to static function. Then make sure that's again on top. And now you can again use partial tool to edit waveguides that you have in this chip. So let's actually make more changes now. So have it be like this. Introduce a new vertex here. Open the ref points. So you can actually see how to align the endpoints. And then place one here, and then place one here. And then when we run the macro, it will snap those correctly. And then maybe adjust this a little bit like this. And then introduce the splitting points. So we have put 1 point here, and then we put 1 point here. And then we use the edit nodes. And if you remember, there was this air bridge that we got rid of, but we can actually place other elements as well. For example, we could put like a smooth capacitors in between this waveguide here. And also another thing is that you can also edit the parameters of this element right here. So if we introduce finger control equals 4, it will also edit the shape of this smooth capacitor. But this is not something that we want. We want to have waveguide coplanar splitter here. So now that we have a splitter, we can then branch off another waveguide to connect to this qubit. And then also we want to edit this node as well. Let's have another splitter here. If it happens that it actually doesn't align correctly, it was a bit of a coincidence that it made the split into upward instead of downward. If it actually is turned upside down for you, then what you can use is this angles parameter, and then it kind of gives angle for each of the ends of the splitter. And since the splitter has 3 ends, then it has to have 3 values. So if you put like 0, 180, and 90, then it will point it downwards. But since we don't need to do that, then we can just leave it as blank and have it here. Okay, so we can now probably save this progress. So we use this macro again, we run this, and since the only thing we did is we made changes to this one waveguide, we can just copy this one line here, and then replace that one waveguide composite cell that we inserted with these new parameters that we've defined for it. And then this should really be the only change that we did for our chip. So we run this this shortcut again, and we should be able to see the splitters in here. And I guess another important thing here is just to kind of there's one problem is that this waveguide composite doesn't introduce the correct ref points. So to do that, you actually have to give an instance name to this waveguide composite. So if you actually in the code put this inst name into like probe line, for example, as an argument, something that you want to be included in this waveguide composite when you insert the cell, just a parameter value, then it will actually introduce the ref points that you can see here. If you open this top ref points layer here, yeah, I guess it doesn't show it. Maybe I have to do this again. Show this as new top, and then cell, convert cell to static, and then show as new top. Okay, maybe now it will show. No, it doesn't seem like it's showing it. Okay, well, what was supposed to happen is that this would have like this. Oh, okay, I actually know why. So you also, what you would need to do is kind of give instance names to these splitters as well. So if we give this one like T1 instance name, and then this one we give T2 instance name. And then we go into this macro again and export the cells. We copy this. We only make changes again to this one probe line. Copy this one here. Then open again. Hopefully now the ref points are going to be visible. And this is just something that, okay, there's now a problem again. We'll import a key error. Okay. Maybe just in the interest of time, I'll just kind of replace the actual working code that I have prepared for this demo. So kind of using this kind of workflow, what you can end up with is something like this. Here, so we would have like this splitting off from the probe line, connecting to each qubit separately. And then I did some tinkering here where I introduced these this phase changing elements here, like a connector that connects from the bottom substrate into the top substrate. I can show you here. Convert cell to static. Yeah, this flip chip connector RF, which is like an element that makes sure that as waveguide is first defined on the bottom chip, it then jumps into the top chip where our qubits happen to have, and then it connects to the qubits on the top chip. This is something that you can do in our tooling. Just make sure that your connector has this parameter named face ID set to 2B1, and it will do that for you. For example, if we remove this here, then it will just be like this on this one side. Let's introduce that here. Another thing is that I've introduced these meanders in this waveguide. This is something that you can edit by setting this length before to some value that is longer than the actual flight distance between these two vertices. So if I increase this, then it will increase the meander as well. And this is something that you can do automatically as well. Another thing is that if you actually look at the code, what I did is that there is also, in the way how these waveguide composites are defined, is that there is this length before set to some value. Actually, let's have a look here. Okay, interesting. So these are things that you can actually parametrize. So instead of using just a plain value in here, what you want, if you want, for example, if you want a way to kind of tinker with this geometry, for example, when you're sweeping parameters during simulations, or you just want to edit the chip while you've opened it in the K layout, then instead of using this plain value, you can actually use the self.left waveguide length. And then the same thing you can do is replace the plain value for the second waveguide using this self-right waveguide length. So now when you have that set up, I can show you what that changes. So when we run this, now instead of using this edit node tool, you can change the parameters of the chip itself. Here I've introduced this left waveguide length and right waveguide length, and instead of 1200, we can set it to 2000, and it will edit that immediately here. Yeah. And a way to use to turn your chip from one phase into a flip chip device is that that's something that you can edit as well from the parameters. So we have this. Let's see here. I think it was frames enabled parameter somewhere here. So here it's set to 0 and 1, and you can actually see it from this code is that I explicitly set it to this list having 0 and 1. But by default, this is just 0, just one element in the list. And that makes it so it's just a one chip device. But if you want to turn it into a flip chip, it's just as easy as just having this. And it will introduce a second chip frame. And all of the parameters of the frame width and height, this is also something that can be adjusted, as well as the frame marker positions. And I guess another useful feature, that's something that we can do automatically, is that we can introduce grids into the empty spaces of the chip. And it's just this width grid parameter that if you turn on, hopefully it doesn't take too long, it will generate these rectangular gaps all over the empty spaces of the chip, which you can see if you then turn on this ground grid layer. You will see these rectangles, and this is something that I understand that is useful in the fabrications. Somehow makes the electrical fields more useful and kind of more predictable, I guess. And it also generates it for the second chip as well. Okay, so how are we guys on time? Would you still want to see how we can take this chip and export it into a wafer layout, or would you guys want to see some simulations that we can do?
Yeah, actually, can we take a quick look at how to do the simulation? Presumably, yeah, there's some way to get the compact models from these simulations with the design you have, say for this circuit or different one?
Yeah, I think we're gonna have to use like some other ready-made chips because I probably don't want to run the simulations during this demo since they take some time. But I can show some of the simulations that are pre-made and show how you can look up the results from the simulations. But okay, so I'll focus on the simulations and maybe this mask layout export feature is gonna have to be left for some other time. Okay, so this simulation export utility that we have here is something that we provide as a command KQCSim. And if you put ls, then it will show you all the simulations that it has currently detected in the folder. And all the simulation scripts are placed in this scripts, like this KDA package Python scripts folder, and then simulations. And here are all of the simulations that you want to use. So maybe like a very lightweight simulation I can actually run live. So let's run this waveguides sim compare. So there are multiple stages. What goes into running a simulation first is that it formulates the geometries in K-layouts and then detects which parts of the geometry is metal and which ones are gap. So here in, it also does parameter sweeping. So in this simulation example, we've done the sweep where we have one simulation where we only have one waveguide, and then the other simulation where we have two waveguides. It actually just uses the waveguides that we've had in our element library, but it also introduces these new layers that were not here before. One is where it detects there's actually signal, there's actually metal coming through, and this is separated from the ground metal that is all around. And then we have the gaps, which are pretty much the same as this base metal gap layers here. And then there's a substrate and vacuum layers as well. They pretty much just encompass the entire simulation. So first, we can have a preview of what the K layout generates, make sure that all the geometries are correct. So now once we close this window, we'll actually see the actual generation happening. So in this simulation stack, we're only using the open source components. So our meshing tool is Gmesh, which is an open source tooling for meshing our simulations. And we've configured the script so that it actually previews how the meshing looks like. So here, as the mesh gets more tight, as we get more into like the signal part of the waveguide. I don't know if this makes sense to you, but this is like the mesh that the simulator will work with. So once that meshing is configured, it will run the actual simulator component called Elmer. This is an open source simulator software that's being developed by VTT, which is like a company that works across the road from us. And it's also interested in doing open source products because it's a non-profit organization. So now we're done with the Elmer simulation and we can actually see the results. So this is a ParaView program with which you can see the energy distributions and the like that were simulated on these waveguides. And since it's the first sweep where we only had one waveguide, we can only see one waveguide light up here. So now it will proceed into running this simulation for the second sweep where we had two waveguides. So here it will show the meshing of the two waveguide simulation. Then it will run Elmer again. And then we will see the results of the electricity the field distribution when it comes to two waveguides. And this is the third-party simulators are kind of interchangeable. So you can use Elmer, but we also provide support for ANSYS if that's something that you're more familiar with. I just don't have ANSYS installed in my system currently, so can't really demo using that. I guess it got stuck a little bit with simulating the two waveguides system here. My computer might be a little bit slow because I'm using virtualization just to kind of have separate files for this demo. But okay, this is kind of the nutshell of how like the workflow works when we run simulations. So then I'll kind of show, so here you can see that you have this one first waveguide and then second waveguide simulated and the results for those. Okay, so this is maybe something that's not super drastic, but I will show some of the simulations that I've run in advance. So with Elmer, you can do capacitance simulations, and we've also recently provided support for S-matrix simulations. So I'll show some of the results that you can get. For example, one thing we did is that we took this qubit that we have that we had in our chip called concentric transmon, and we can actually have a look at what k-layout we did for it first in this first stage. So there is this simulation.oas file. Here I want to show that we've done some sweeping. So we took this this qubit class codes, and we adjusted some parameters to have a sweep of those parameters. So you can see that here it kind of varies in its shape a little bit. So this is if we want to do some kind of study that how does capacitance correlate with certain features of this qubit. And there's also like multiple features here, I guess. One kind of only changes the this outer rim location of the qubit, but then the other one increases the central island radius, for example. So we're kind of doing a study of like of multiple as multiple features change. And I guess some other stuff here as well. So once we've done all of the sweeping, then all of these results are kind of placed in for each case separately, and we can run ParaView on them and see what that gives us. So if we open this concentric transmon and this PV2 file, and then it was points here. So this tells us something that if we provide like current into this one coupler of this qubit, then what parts of it light up. But maybe for more of a data-driven approach, instead of looking at pretty pictures, we have this project results JSON, and this gives us like the C matrix values that could be useful for you to validate that your qubit, what kind of capacitance properties your qubit has in its different configurations. So this is one for like 100 to 70, whatever these parameters meant. And then here's one that has, I guess, different values. So you do like a sweep of different parameters, and then you can get the capacitance values for each of the values of these parameters. And then in some external part of the code, you can then draw a graph and then see a correlation on what features affect the most to the capacitance of your qubit. And then another example that I can show is we run like an S-matrix simulation on a full chip. So let's see what the geometry looked like when we exported the simulation. So this is like a fully connected chip. It has launchers, and then it has these Swiss-Mon qubits connected to it. Each qubit is coupled with like a resonator of a certain length, so that these can be then read from the readout. And then using we recently added support to Elmer, so you can run this S-matrix simulation. We used to only do it for ANSYS. Yeah, let's run ParaView again to just kind of visualize what things light up. ParaView here. Then we open this full chip, resonant VTUs. Something like this, you probably have to pick like an electric field. And so I guess here we sent a signal to this readout that captures like reads out all the qubits that are connected to the probe line. And I think there was like a one drive line that was activated as well for this qubit. But the more kind of data-driven results can be read from this project results file here. So it will show you like this S matrix and then all of the values that are needed for this.
Yeah, just one sec. So this is the scattering matrix. But what are the what are the units here?
So I'm not actually sure because I haven't done like too much simulations, but if it's S matrix, then it's my understanding is that we simulate how like the signals bounce off as they're being introduced from one launcher, then how it kind of reflects back. So I'm not sure what would be a unit for this. At least for capacitance, I know that is the Faraday units, but I'm not sure what this with this matrix is. But
okay. Yeah. But in that example, for instance, like how many ports do we have? Like, so there's the input and output ports when you're defining.
Yeah, I think for this simulation, what we actually configured is that the ports are for every launcher here, so 8 ports here. But this is something that can be easily configured. So if we actually have a look at the script itself, we have here, and this kind of sets the parameters, but then also if we have a look at the class itself, and then we actually see how we've placed the ports. And in here, we have edge ports that we've put for every launcher. So I imagine if you would actually like remove some of the entries here, I believe here the readout would be west north ports and then east south ports. So what you can do is that you keep only the west north and then east south ports here. And then if you would rerun this simulation script again, then it would only send simulate electricity only coming from these two ports.
Right, and there should be like checks on whether the S matrix makes sense, right?
Yeah, I guess this is something that you kind of have to carefully make sure that they correlate with the ports that you define.
And what's depicted here is, let me take a quick look. Electric field magnitude. So this is magnitude, not magnitude squared. I mean, it's fine, but I'm just making sure I'm interpreting this correctly.
Okay, yeah. This is probably I cannot provide like too much information on because I haven't really studied simulations as part of me working in IQM. But there's seems like there's also these things that ParaView provides. Not sure if heating is something interesting, but magnetic fields as well, just potential.
Oh, okay, and this is just using external plugin.
Yeah,
Oh, okay.
this is not strictly part of KQCircuits. It's a visualization tool that KQCircuits works best with. These are something that could be, with relatively small effort, be interchangeable if there are other visualization tools.
Fascinating.
Okay, so that's pretty much all I had on the simulations. I guess if you guys want to call it a day, then I can probably stop here.
Okay. Let's stop recording now.